part C.2, examples of asymptotic notations, part 1. Yeah. In this part, I will show many examples. All right, the first one, it looks pretty simple, but we will use definition to prove it. You need to write the proof. Show that n plus 2 function belongs to big theta of n. Very simple functions, both f of n, g of n, very simple. Okay, the only difference is plus 2. That's the difference. Okay, yeah. So when we show the proof here, we can use two methods. The first way, definition, directly, based on the definition. Second, we just take the limit, because for the asymptotic notations, big theta, there is a limit way to describe it. So that way also very easy, so we can also use that. All right. Here, so let's look at the definition way first. This is the given function, f of n. And for this function, in order to apply the definition, we need to get a C1, C2, right? Two positive constants. C2, g of n, that's the lower bound, comparing with f of n. And C1 times g of n, that's the upper bound for f of n. Okay? So we need to find these two constants. How to find it? First, we can see n plus 2 greater than n, right? Plus 2. Because you're plus 2, it will be bigger. So we drop that plus 2, the function value will be smaller. Okay? And here you can see, because n, that's just a multiple of g of n, right? So positive constant multiple of g of n. That satisfies our lower bound form. When this inequality true, when n greater or equal to 0. Because n, that's our problem size. When we consider n, problem size should be greater or equal to 0, right? We never consider negative problem size, right? It does not make sense. No. So that's why when n greater or equal to 0, we have this inequality. Okay? And we can say our C2 constant equals 1. So we find C2 constant first. Then next, this time we want to look at the upper bound side. Okay? We want to use a constant multiple of n to control from the above on top of that f of n. So in order to get that, we want to replace constant 2 by a constant multiple of n. Let us use just n. Okay? We change from 2 to n. Can we make the value larger? Most of the time we can, right? But if we put some condition, n greater or equal to 2, then we have no problem. Under n greater or equal to 2 condition, then n expression is always greater or equal to the constant term here. How about that? That's what we need. Then we can simplify n plus n, that is 2n. Okay? So another constant multiple of n, but this time from upper side, right? So that gives us C1 constant. C1 equals 2. Okay? Then, after C1, C2, we need to get that n0 number. So what is our n0? Because we need both true, n greater equal to 0 true, n greater or equal to 2, also true, both true, then we pick the larger constant number there for n0. We make n0 equals 2, then when n greater or equal to n0, both inequalities true. Yep. So, all right, how to prove? By definition. When I give you such question, I ask you to prove by definition, you need to tell me this. You need to find the C2 constant. Then you need to find the C1 constant. Okay? To give me the inequality. Also, you need to give me the n0 values. Okay? If you give me all these important pieces, then you solve the problem. Okay. All right. So here, let me just, this question can also be proved easily by the limit, by calculating the limit. Yeah. That will be much easier than this way. Okay. Much easier than this definition way. Okay. Yeah. If I do not ask you prove by definition, you can use the limit way to prove. Okay? The limit way, you just do this. You calculate this limit. n plus 2 over n. Can you find that is equal to 1? Right? 1, it is non-zero constant. When this is a non-zero constant, your conclusion is n plus 2 belongs to big theta of n. That's simple. Okay, so that's the limit way. Yeah. All right, the next example. Prove n cubed belongs to big omega, this time big omega. You only do the lower bound, big omega of n squared. Okay, that's pretty easy, pretty straightforward. Just do the big omega, lower bound side. Yeah. Lower bound, we can write this n cubed greater or equal to n squared for n greater or equal to 0. 0, they are equal. N equal to 1 also equal. When n greater than 1, strictly greater, n cubed strictly greater than n squared. Okay? So we know it's true. So then we get a constant c equals 1. And n0 equals 0. So we prove it. Okay? We prove it. Yeah. But if you want to use the limit, you can also, this question, you can also use the limit way to prove it. If you want to use the limit way, you can use this. N cubed over n squared equals infinity. Then, right, actually, infinity, so you can see, because, actually, first, this is true, right? This is true. How do we connect to big omega? Because infinity, we can say infinity greater than 1, right? Greater than any positive constant, greater than 1. You can choose greater than 100, you can say, right? Infinity, you can say greater than 100 when n is sufficiently large. Sufficiently large. Okay? Then your conclusion, because greater than this one, you can connect to big omega. You find the lower bound, when n sufficiently large. Yeah. So if you like, you can also do that way. Okay. All right. Now, example 3. Show this function n plus 2 parenthesis cube belongs to big theta of n cube. Yeah. First, let's still use the definition way. Lower side, upper side, right? N cube, that's easy because we drop positive constant 2, right? Yeah. When n greater or equal to 0, we can drop it. Yeah. And the C2 equals 1. Yeah. So it's trivial. Yeah. But from the upper side, we replace 2 by n and try to make the whole value larger. So we need to put a condition, n greater or equal to 2. Yeah. So that 2n, n plus n 2n, the whole thing, we need to cube it. Yeah. Cube, take the cube operation, 8 times n cube. Yeah. So that tells us C1 equals 8. Yeah. So then n0 equals 2. Yeah. So we prove it. 3 pieces, C1, C2, n0. We find them, and we get an inequality. Upper bound, lower bound, following the definition. Yeah. But if, so you can also use the limit way to solve it. Yeah. The limit way, this time n plus 2 cube over n cube. Can you find equals 1? Equal to 1. The limit equals 1. Then big theta. Yeah. Easier than the definition way. Yeah. All right, so that's number 3. Number 4. Number 4, log of n belongs to little o of n. This log, we can assume some positive base, greater, the base number greater than 1. Yeah. Suitable base. Yeah. But here, for this case, we may need to use the limit tool, the L'Hopital's rule. L'Hopital's rule, so we need to make sure we use the continuous variable. Here, n, it's a discrete variable, so we need to replace it by the continuous variable. Then we can apply the L'Hopital's rule. Yeah. All right, so let me do it using the L'Hopital's rule. Why? We can apply the L'Hopital's rule here on ratio of 2 functions, but the variable x is a continuous variable. Okay. The reason here is because it is infinity over infinity indeterminate form. Limit over infinity over infinity indeterminate form. So that's precondition for L'Hopital's rule. All right. Then we can take the derivative. Yeah. Hope you know the formula of the derivative of the logarithm. Yeah. Because here we use some hidden base a that is greater than 1. Okay? Because when we take the derivative, we need to use this number. Okay? Yeah. All right, so the numerator, its derivative is 1. Denominator, you can find the formula from web or from, some calculus textbook. Yeah. 1 over natural log of a times x. after simplification, you can see when x goes to infinity, this limit is 0. When the denominator goes to infinity, the whole fraction goes to 0. The limit is 0. Yeah. When you have this 0 limit, f of n over g of n, yeah, because after this continuous variable way, then we can switch to the discrete variable. Log of n over n equal to 0. Okay? This tells us little o. Tells us this little o notation. It is true. Yeah. All right, so that's question number 4. Next one, number 5, n to the dth power. So this dth power, here we assume it is an integer for convenience. Later, we can drop this condition. Later, we drop it. Because we don't need it. We only need a positive number. That's it. Any positive number, this result is correct. But when we prove it for integer, it will be easier. If a non-integer positive number, slightly harder, but we can handle it. Later you will see you can handle it. Okay? You can handle it. All right. Now, let us prove it. We use the same way of the previous example, L'Hopital's rule. This time, we just do it, okay? First, we replace the discrete variable by continuous variable, x, okay? Then we notice, we check, it is indeterminate form, infinity over infinity. So we can apply the L'Hopital's rule. When we apply the L'Hopital's rule, we take the derivatives, numerator function, denominator function. Numerator function, we use the power rule. Remember, in calculus, derivative, there is a power rule. We can apply d, the exponent number, so we multiply that constant d, yeah, x to the, this time it's power, exponent number reduced by 1. That's the power rule, okay? Yeah. So, and exponential function a to the x, its derivative is this one. Yeah. All right, so then, after that, you can see if d greater than 1, this is still infinity over infinity indeterminate form. So you can apply L'Hopital's rule another time. Okay, another time, yeah. So if we apply another time, so this time you can see d times d minus 1. The exponent number is brought down another one, d minus 2. Okay, d minus 2, yeah. So then denominator, you multiply another log, natural log of a, yeah. And so on. You keep doing that. If d is still greater than 2, you can keep doing this until you reach a point the exponent number becomes 0. Then it's not an indeterminate form, right? So when the exponent number becomes d minus d, that means you apply L'Hopital's rule d times. Yeah. When you apply d times, the exponent number is reduced by d. So d minus d equal to 0, x to the 0 equals 1, right? We know that. X to the 0 equals 1, so it's not a variable, it is a constant. When it is a constant, so this form, it is not an indeterminate form. If it is not indeterminate form, we cannot apply L'Hopital's rule another time. So we have to stop here. We have to stop. Okay? All right, so let's clean up a little bit. We get d factorial over natural log of a, parenthesis, to the dth power times a to the x. Okay. So this one, when x goes to infinity, it is 0. Thus, we get that little o notation, conclusion. So little o notation. Yeah. All right. So that's the example number 5. Example number 6. All right. This time, log base 2 of n belongs to little of square root of n. Square root of n. Okay. We can still use the L'Hopital's rule. Okay. Look at this limit. Infinity over infinity. Continuous variable x. Then we take derivative. Yeah. So we write root of x to the 1/2 power. Yeah. Then, after the derivative, power rule, this power rule, okay, power rule, yeah. So that is, if xp power number could be positive, negative, right? Even positive, negative, you can use it, okay? Yeah, but not 0, okay? 0, that's constant. You take derivative, that's 0, okay? Yeah. All right. Power rule means when you take the derivative, you get p, the power number, whatever, exponent number, whatever it is, no, times, but not 0, yeah, x p to the p minus 1, that power. All right, so here we use it another time. We have this. Simplified a little bit, you get this expression. But this one is not an indeterminate form. It's not infinity over infinity indeterminate form because the numerator is constant. So in this case, when x goes to infinity, the whole fraction goes to 0. Its limit is 0, so you have that little o notation. Okay. All right. Next one. Example number 7, and this time show that natural log of n belongs to little of n to the d power, so that d will only require positive number, any positive number. Okay, integer, not necessarily integers. Okay, yeah, even small fractional numbers also fine. Very small number also fine. If only it is positive. If only it is positive. Okay? Yeah. So later you will see sometimes we may pick 0.00001. If d equals that, this is still true. Okay? Even that d is a very small positive number, this result also true. Yeah. To prove it, L'Hopital's rule. Okay? Yeah. Take derivative. It's infinity over infinity indeterminate form, so we can apply L'Hopital's rule. After taking derivative, the power rule, bottom, natural log, derivative 1 over x. After simplification, you can see it's not an indeterminate form. Numerator is constant 1. determine x to the d, because d is positive. Here, d is positive, so dx to the positive dth power goes to infinity, right? When x goes to infinity, it also goes to infinity, so the limit is 0. If the limit is 0, little o. So we go back to n. Log of n belongs to little of n to the d. All right. Question number 8. So this one is much harder. So for this one, we need to show n factorial belongs to little o of n to the nth power. N to the nth. The harder part is n factorial. How do we describe n factorial? That is very difficult. But here, in order to handle the n factorial, we need to use a special formula here. So what's that formula? Stirling's formula. Stirling's formula. So what's that Stirling's formula? The Stirling's formula gives us some nice way to approximate n factorial. This version, the first version, n factorial approximately equal to this expression. This expression. So you can see it is easier to handle than the original n factorial. The original n factorial, we have no idea how large it is. Okay, so this way, so we feel a little better. Okay, a little better. But this approximation sign, we feel not quite convenient to use. Not quite convenient when we want to prove by definition upper bound, lower bound, because this approximation does not tell us upper bound, lower bound, right? We don't have that information, upper bound, lower bound. So we need another version of the Stirling formula with upper bound, lower bound, specifically. Okay, Here, this version we can use. So we have a lower bound version, expression for n factorial, and we also have upper bound expression for n factorial. So when we have both expressions to approximate n factorial, then we can apply our some math tool to solve it. Here, because we spent a lot of time, so let me stop right here, and in my next video, let us complete the remaining part. All right, so let's stop.